Go ahead and get started for our last lecture on the Verity project and trying to formally verify implementations of distributed systems. So just as a reminder, remember, so our goal was sort of starting off to figure out, how can we formalize what it is distributed systems do, right? How do we get the ideas about distributed systems from our heads into a buffer and Emacs that we can do proofs about in Coq? And then the key mechanism that we've been talking about the past couple of lectures has been these sort of transformers, right? So that we can sort of decompose, we can separate reasoning about our application and its correctness. Things like, a key value store is really a good map, kind of like what Andrew was talking about earlier, right? Some key value store has those properties. And the fault tolerance, so that, even if messages get duplicated in the network, I'm not going to accidentally, update a key when I shouldn't, things like that, right? So we can sort of tolerate different kinds of failures. And we want to tease those apart so we can just apply a transformation and take a system whose application has been verified to be correct in a world without failures and get one that will still be correct, but even in a world that has more failures. So we're going to just really quickly do a review, high-level conceptual idea of what we saw last time with Verity. And then what we really want to do today is talk more about sort of the marquee system, the big proof effort that we had so far in Verity, which is an implementation of the Raft consensus protocol. But in particular, after we'll kind of look at a few Coq buffers to do that. But I wanted to have a discussion with you all about sort of the challenges of verifying these big systems and some of the things we learned along the way that might be helpful to you if you go out and try to do something similar. So starting off with Verity, right? Remember, whenever you try to verify a system, the name of the game is finding the inductive invariance, right? You should be able to write down what you want to be true at the end of the day, what clients should see, what they should experience, but that's almost never inductive, right? So you have to find some stronger property that's still true initially. It can't be too strong, it can't be false. So it's still true initially, and it's strong enough to imply itself after every step, as well as the original specification that you actually wanted. And the problem, right, was that we don't want to do that work and try to reason about fault tolerance at the same time. So we introduced these different verified system transformers, right? And last time we talked about sequence numbering and we talked about the primary backup system. And today we're going to talk a little bit, mostly we're going to talk about Raft. And we'll also see things like ghost transformers, which were important to enable the verification of Raft in Verity. And as always, right, if there's any questions as we're going through stuff, please don't hesitate to holler. Okay, so what the heck is Raft? So Raft is protocol. It's a distributed system that we use when we want to tolerate machines crashing, sort of at a high level. And so, suppose you have some system and there's some particular node, right? You have some service you're providing, and there's some particular service, component within that service that's really important. So one thing you can imagine is like a lock server, right? If the lock server goes down, then all the clients who are doing their own work can't coordinate, and that'd be a bummer. Or the metadata for a distributed file system, right? So there's some key component that you really just absolutely, positively can't have fail. So basically what Raft tries to do is replicate it, right? The idea being that as long as at least half the nodes haven't crashed, that component will continue to provide service, right? So again, we're sort of doing this simulation, right? We're trying to construct another version of the system that does the same-ish thing, but in a more adversarial world. So the first thing we need to do is figure out what does that mean. So does anybody have an idea for what the specification might say for Raft, or why it's tricky? So before, right, we had a single node, some service, some stateful function basically, and clients could ask it to do things, it would do it and then respond. And now what we want to do is we want to tolerate crashes, right? We want it to be the case the service still survives if one node fails or up to half the nodes fail. So we built a bunch of copies of it. They're going to coordinate and provide the same functionality, the same service to clients. What might be tricky here? What are we going to specify?
Well, you sort of got two different languages, because one is the language you care about for the clients, and then the other is the language that discusses failures and so on the internal nodes. You got to paste them together.
Yeah, so that's right. So one thing is, right, we have there's going to be new kinds of messages to deal with this coordination between the replicas, right? And what we want to do is we want to make sure that when we set that up, we do it in such a way that whatever we end up with is similar to what we started in. Right? So what's tricky? So one of the things that's tricky is that here, right, this node just can immediately reply to clients. It gets a request, it does whatever it was asked to do, and it acknowledges it, right? It gives the answer back. But here we have to be a lot more careful, right? So here, before I reply from this replica, I better make sure that everybody's on the same page, right? Before I tell the client, like, yeah, I did that for you. Like, acknowledge you have the lock, or, you know, I stored I associated that key to that value, or whatever it is. You want to make sure that if some other client is talking to another replica, they don't get an inconsistent answer, right? In this world, you sort of got consistency for free, right? There's only one node, so of course all of its state is consistent. But now when I have multiple copies, I can get into trouble, right? So suppose that two clients simultaneously ask two different replicas to do conflicting operations. If both those replicas do the operations, now we're really sunk, right? Because the state of the system is no longer consistent. So what we want to do is we want to provide, remember the goal is to simulate. So we want to have these internal messages, this way that these replicas coordinate, add up, so that to all of the clients of the replicated system, right, they get consistent answers as if they were talking to a single node, right? So this property broadly is called linearizability, right? And it basically means that the sequence of interactions that clients experience from interacting with the replicas could be explained by a single node running, right? The clients can't tell the difference just based on the I/O behavior they got from interacting, with the replicas. The difference between that and interacting with a single node. Now, that's also not quite true, right? Remember, we said we have to lift our properties, and we're going to get some wiggle room here, right? So in this world, it has to be the case that we can just tell clients, sorry, right? You asked me to do something, but your request is out of date, like, ain't going to do it, or whatever, right? Whereas here, the node can sort of like always reply. You don't have to worry about, remember, handlers are atomic. There's no such thing really as a simultaneous request. So we're going to have to, there's going to be a little bit of wiggle room, but linearizability can sort of encompass that. Okay, so how are we going to do that, right? So here we're going to have a cartoon version of the implementation of Raft. We'll briefly look at the cock buffer to show you how it ends up looking in Verity. But essentially we're going to take as a parameter a state machine. And here I'm using CMessage for client message. It's just like our input and output type we've been seeing. Don't worry too much about that. So I'm going to define a system. I'm going to be parameterized by a state machine, some stateful function that I want to replicate. And I'm going to maintain its interface, right? I'm going to have the same input and output types that state machine had. And then we need to figure out, okay, well, what are the other message types and the types of data, additionally, that our nodes are going to store when they try to implement this protocol. And then what the heck are they supposed to do, right, when they interact with clients, right? What is this sort of internal set of transitions that happen to provide this service, to provide these replicated state machines? So to do that, we'll talk about how Raft works, again, at a pretty high level. So Raft executions have this structure of an infinite sequence of terms, where each term is divided into two phases, right? An election phase and a replication phase. So in an election phase, what happens is some node tries to become leader. All right, so at the beginning of time, nobody is leader. And if you haven't heard from the leader, and after a certain amount of time, a timeout fires, and then you try to become leader, right? So some nodes decided, you know what, like I don't see anybody around here with real leadership potential. I think I should be in charge. And so this candidate sends out a message to all the other nodes in the system. Remember yesterday when we saw in Verity systems, the systems we've been looking at have the ability, they know all the nodes in the system, so they can sort of broadcast, right? So this candidate's going to broadcast to all the other nodes in the system and say, hey, please vote for me to be leader, right? And the candidate already has one vote because everybody's going to vote for themselves. Everybody has a lot of self-confidence in Raft. And then what happens is, ideally, from the perspective of the candidate, all the followers respond, yes. And as long as the candidate gets more than half the votes, they indeed become the leader, right? Now, it turns out that actually the replication phase is extremely similar. And so what happens in the replication phase is that clients interact with the leader. They make a request, right? And what the leader is going to do, the leader would like to tell the client, the external client, like, yeah, I totally, what you asked me to do is done, and it will always have been done. You're never going to get an answer from another replica that's inconsistent with me having done this action for you. But before the leader can reply to the client, it needs to actually make sure that's true, right? It needs to make sure that for all time, all responses anybody gets from any other replica will be consistent with the leader having done that action. So it does the same thing, right? It basically holds an election. It tells, hey, all the followers, we're doing this, right? And the followers reply. Once the leader gets at least n over 2 responses, it knows that that entry, that operation on the state machine has been committed, right? And that's durable. That's not going to change. It's going to last forever, right? It will just always be true. Okay, so we want to build the system. What we do is we take these cartoons and we translate them into Galena, and we end up with something that we can actually run. And we can look at that really quickly. Let's see, here it is. So we have some parameter for the number of replicas, something about the input and output types for the state machine, stuff about the clients. And then we're going to have a log, right, which is a set of operations that have been applied to the state machine. So we have these make entries, this make entry type. Let us know like who did it, where it is in the log, this kind of stuff. We have the messages, the input and output types. We have the types of nodes in the system. And once we have those, this is kind of like our base params from SimpleDS. We have some helper functions, and then here in a minute, we're going to see some handlers. Let's see. Where did that go? Lots of helper functions. Here we go. All right, so here we have the message handler. And what it does is when it gets a message, it sees what kind of message it was, and then it sort of calls the appropriate helper function to do this sort of election style thing. And those are all defined up above. And then below we also have handle input somewhere. But you get the idea, right? So there's a lot more code than the kind of stuff we saw in SimpleDS, which was, here's like handle client request, right? So depending on who it's going to, it responds differently. In this case, actually, what happens is if a client makes a request to anybody other than the leader, it does nothing. In practice, you would probably try to forward the client toward the leader or something. Although the problem is that you might be out of date, so there's no guarantee. But only the leader actually tries to orchestrate operations happening. But anyway, the high level, right, is that while there's a lot more detail and the system's more complicated, we're doing these sorts of elections, the structure of this is really just like SimpleDS, right? We've got some base types. We define some functions that are event handlers. They're in this handler monad, right? But everything just kind of works, right? It's just sort of scaled up. Okay, and then the other thing that we wanted to look at real fast, let's see. Let's go ahead and just bring it up now. There's also a theory in Verdi of linearizability, right? So again, right at the end of the day, what we wanted to say is that the sort of trace of I/O events for the replicated system is, if you can linearize that to a trace of the single node system, right? So here we have, let's see, how long is this? There's a bunch of limits here at the bottom. This is like weighing in at not quite 1,500 lines, right? But we end up with a description here of linearizability. Oops. And we'll see how that gets used in a second. So one question though, so there are a bunch of limits in here, but with linearizability, right, is this something that we can get wrong? Or because we are virtuous proof assistant users who are getting QEDs on everything we write, there's no way we can screw this up?
This is your specification. If you get this wrong, you prove the wrong thing.
Yeah, so for Raft, right, for the system transformer for Raft, the whole point, the whole game we're trying to play is trying to build these, we're trying to replicate this node and ensure it has this linearizability property. So if we do this wrong, we got the spec wrong, we made a mistake, our verification doesn't do what we think it did, we're in bad shape, right? We've shown that our implementation inherits the bugs of the specification. That's what we've ended up proving. Now, you know, because the spec looks a lot different from the code, it's probably unlikely we make the same mistake in 2 different places, et cetera, et cetera. But there is one other saving grace, right? Which is that this is the final spec for Raft. But when I actually build an application that uses Raft, I'll probably have some top-level application spec that needs to hold on the final version of the system after I've applied the Raft transformer to my underlying application code, right? And so just like Andrew was showing earlier, right, and when you were looking at the TCB for the verified crypto, one of the things that was neat is that, you know, CompCert sort of got eliminated, right? We didn't have CompCert in the TCB because we used its specs and it just sort of fell out. And we get the same thing with Raft here, right, if we have that top-level spec. So, you know, just like CompCert has to trust its spec, right? Like, that's part of CompCert's TCB is that its spec is right, period. When you build another system that uses CompCert, actually it doesn't necessarily inherit CompCert's spec as part of the TCB, right? You can sort of cut it and eliminate it. And we can play the same game here. If we get linearizability wrong, our Raft implementation is wrong. However, we have a bigger system that uses it, we might be able to eliminate the Raft spec because we have some top-level application specification that we're using that we're going to prove. Okay, so you know, this is what we want to do. And it turns out we did it. So let's go to here. So if we go up to the top, so here we start importing a bunch of stuff. And then we start giving a bunch of hints about how to instantiate different type classes. And then finally we get the proof, right? And so basically, as long as sort of the clients, so there is a assumption that clients are sort of following a protocol that they, you know, clients don't spoof other clients' names, stuff like that. And basically, we just show that whatever happens in the wrapped system is something that could have happened in the state machine, right? So clients can't really tell the difference. Yes?
With the idea of kind of intermediate states being more important, I'm just wondering, so in like a more higher level state, if you kind of use the definitions from an intermediate level state, does the kind of the notions that they define, are they still important in terms of understanding that higher level state is correct? So does it go away entirely or not?
So I'm really hard at answering questions on my feet, so I'm going to take a stab at repeating that to make sure I understand. So we've got this idea that we can kind of eliminate trust on intermediate specs. And now the question is, suppose that your higher level spec, though, depends on notions from that intermediate spec. Have we really eliminated all of our trust in that intermediate spec? Yeah, so that's a great question. I guess the answer is sort of yes and no, right? It's no in a technical, it's yes in a technical sense. Like we have eliminated our trust on that spec. Now, if we reuse definitions, right, if our final top-level spec includes definitions that were from that, you know, we still sort of, you know, our spec, we have to take like the transitive closure, all the definitions that we use when we define our specification. So if we reuse those definitions, they're still in there. That's still part of our spec. And, you know, we didn't eliminate those parts, but that's just always true about specs. Now, there's another answer in the sense of, you know, no, like or yes, I forget which way the question went. But we also, so in some sense we've eliminated it, in some sense we haven't. I mean, the sense in which we haven't, right, is that our own understanding, the way that we intuitively think about what the system might be able to do, the way we explain it to other people, right? So remember, at the end of the day, it's really cool to prove systems and to go and talk to your friends about it and have fun doing proofs and to actually run stuff and get, you know, people from the systems community excited and to get papers. But really, at the end of the day, our goal is to convince, you know, users, right? To convince other humans who are doing things they don't want to have fail. And so if we have a buggy understanding, even if we've sort of eliminated it when we explain it, that can be bad, right? We sort of are going to carry that forward. Okay, good question. So anyway, so here it is. We did the proof. And we'll talk a little bit about why there are so many imports and all this about type classes and whatnot. But you know, this is really it. We got the QED here. This really establishes that Raft is linearizable. It was a very great day when we got that QED. But on the way there were some days that weren't so pleasant. So what was unpleasant? right? What's the problem? When I'm going to go prove Raft, prove this